think we almost reach here, right? And we keep continuing to discuss the property of Pauling matrix. Then we are going to do some of exercises. Example for the spin envelope of the momentum. We discuss or introduce the spin since we know that it's intrinsic of this fundamental particle. Essentially, each fundamental particle has a spin. So we introduce the spin operator and the angular operator, and then we consider one case for spin equal 1/2 case. So for the quantum number s is fixed, then the ms is from minus s to the plus s, right? So we have only two of it, plus minus half. Then the corresponding the eigenstates for giving s and ms is only have these two choices, either s fixed, either ms plus or minus half. Then we know this, these are general property of the angular momentum, right? So the s square, apply the eigenstates, that give us s square, h bar square s multiplied s plus 1. Then in this case, that is s half, right? Half multiplied half plus 1, so that is 3/4 here, h bar square. Then for s, sz, in general, he gave us the, so it's ms, h bar ms. So here ms has two possible values, plus minus, depending on which eigenstate, right? So if plus is plus, if minus is minus. All right, so that is general. Then we discuss how about the represent this or express operator and eigenstates in the matrix representation. The basis we take these two eigenstates, right? Half, plus half, and minus half. So for any cat, you know in the matrix representation is a column, right? So the columns be matrix element of this vector or cat project to basis. One is ms equal to half, another ms equal to minus, right? So that's the general. By this, then we obtain this vector itself, the eigenstates in the matrix representation is nothing but the column matrix from 0 or 0, 1 for these two. And for any other general, you can do the same thing. So if I give you any arbitrary function, you can find this column. For any operator, we have 4 matrix elements, right? So each one just is the inner product of this, not sandwich of this. So we do this, and for the s square, you will see that is the eigenvalue, right? Because it's diagonal. So this is the eigenspace of s square. So that's the diagonal in this matrix representation. Similar for sz, also diagonal. The diagonal term corresponds to the eigenvalue, right? Plus minus half. 3/4. But for s plus minus, we I didn't write down here, right? S plus minus we know increase 1 unit by or by decrease 1 unit. So we do the same thing here. We obtain this matrix representation of s plus s minus this one. Then we can obtain sx and sy, since this is just simply add this together or subtract. So we have this. Then since in the 2 dimension, what we found, you can see sx, sy, and sz all are same factor here, half h bar. Then multiply another 2 by 2 matrix. So we introduce Pauling matrix. Therefore, the sx, sy, sz actually is just the constant half h bar multiplied the Pauling matrix. Then we discuss the property of Pauling matrix. First properties, the square of any components of Pauling matrix is unit matrix. Example here, for example, sigma x, that is here, right? That is 0, 1, 1, 0, 0, 1, 1, 0. And you can see here, this is 1, right? And this is 0, 0, 1. Yes. So the others you can do same thing, right? You can check. So that is j from x, y, z. You can check yourself. Second one is this we call this is sigma r j sigma k plus sigma k sigma j, which we call this anti-commutation relation, because we use this not square break, is this break, that is definition, this one. And we give the result is, I think I did this class last time, and we can do one example, is 2I third time GK. So, okay, so let's check. If one case is J is X, K is Y. So we have sigma X, sigma Y plus sigma Y, sigma X. This one is if J not equal to K, that's equal to 0, right? So let's see this is 0. Then we have 0, 1, 1, 0, 0 minus I 0, plus 0 minus I 0, 0, 1, 1, 0. The first one, I, right? This one is I. The second one is 0. And this one is also 0, right? And the last one is minus I. Right? This product. And this one is minus I, right? And 0, 0, and I. Yes. Right? You see, they just good results, right? So that is my example to show that. And if J equal to K is very obvious. If J equal to K, this is, for example, x. So this is sigma x squared plus sigma x squared, right? So sigma x squared is 1. Then we have 2, so that is 2i. That makes sense? Okay. So we prove, we just checked whether this relation or property holds. Number 3 is commutator, right? We also see this sigma j, sigma k minus sigma k, sigma j, which is mathematically introduced this commutator or commutation relation between sigma j and sigma k, right? The result is 2I epsilon. We introduce this notation, KL, sigma L. So here, last time is in the class, I didn't explain. Here, please, now let's say when is equal to 1, so if JKL, right, we follow the order, is an even permutation. Permutation of x, y, z. What does mean? If we want to, this order, what is this one, JKL? We want to make this permutation such that in the finals be x, y, z order. How many times? If even, this is positive. Minus 1 is and 0 if there are two identical. So if any the index k, j, k, l, any of them, any of two of them are same. This is the same. Now let's do an example here. Okay. Sigma x, sigma y. Okay. So sigma x, sigma y, it must be, how to select L? Must be z, right? If are x, then that means two of them are same, so it will be 0. So that be I, okay, 2i multiply 1 plus sigma z. So now you can see here, x, y, z, 0 permutation, right? We don't need to make any permutation. That is even case. So this one is case 1, epsilon, x, y, z. And there's no any other. If this is x, it will be 0, right? Because in this case, y also 0, so only z. And since this order is follow this permutation 0, so that is positive. Okay. And just do the inverse. Sigma y, sigma x. So 2I multiply minus 1, right? And sigma z. Because here, we have to select z. If not z is equal to 0, then if we select z, this is y x z. So we are going to exchange x and y primitive, so that is become x, y, z over. How many times? 1 times, right? So that's this one. This is minus 1. That is how you apply this relation here. Okay. I think that is the end of last class. We introduced these properties. Now with these properties, number 4 is easier. So okay. Now here this is sigma. This is sigma j multiplied sigma k plus sigma k sigma j. This is a minus, right? So if these two add together, the second term disappear, cancel, right? So we have this here, sigma j, sigma k, plus sigma k, sigma j. This is a plus, that one, sigma j, sigma k, minus sigma k, sigma j is equal to 2 sigma j, sigma k, right? Here. And that, and equal to the, now this part is this one, right? It's a 2I delta gk, right? Plus, okay, plus 2I epsilon j k L sigma L, right? This is the left hand side. Left hand side, this part left hand side, and this part left hand side are together. Then the right hand side plus this right hand side. So we can cancel this factor 2. Then we have another feature. Is the product of sigma j and sigma k is equal to I delta jk plus I epsilon j k L sigma L. Is property 4? Yes.
Are these the second term and the fourth term in that line? Sigma k, sigma j,
Yeah.
sigma k, sigma j.
Yeah, this one.
Are those supposed to just cancel?
Yeah, this cancel, yeah. Right? The same. This one is this term. It's this anti-commutator relation. Commutation. And this one is commutator relation. So that means the two anti-commutator relation plus commutator relation of sigma j and k, that equal to either twice of this and or this one. So we have this relation. That makes sense?
Yeah.
Okay. Yeah, more properties. Number 4, number 5. Okay. All right. Maybe examples here. Maybe examples that I have to go to number 5. Example is sigma x, sigma y. Right? J equal to x, k to y equal to here. I not equal to j not equal to k, right? So this is 0, right? The first term is 0. Plus I, okay. Which term? If x, this is xy, right? Xy is j, right? So immediately got this relation, right? Then with that relation, now we have a number 5. Now I'm going to use sigma x, sigma y multiply sigma z. Since sigma y multiply sigma x multiply sigma y is equal to I sigma z, right? And then multiply sigma z. Since sigma z square is the property 1, is I, is unity. So the product of these 3 Pauli matrix actually equal to I multiply the unit of the matrix. Right? You just start from this result, and you just multiply. So that is number 5. Number 6. Okay. How about this one? The Hermitian, the conjugate of this Pauli matrix. Pauli matrix, for example, here. How about this one? Spin is Hermitian, right? So if I take this, the conjugate spin also equal to, so they also Hermitian, right? Then now, further, how about the trait? Let's look at the trait. This is 0. This is also 0. This is also 0, right? So trait always 0. How about the determinant? 1, right? This one, 0 and minus 1, the determinant is 1, right? So it is a minus 1, sorry. Look, this one, this is minus 1. This one, 0, minus, this is this multiplies plus 1 and minus 1. This one is minus 1. So that is the property 6. Property 7. Okay. This one, let's just give you the any. If any two the vector operator, just vector. Any two vectors of say A and B commute to Pauli matrix, then we have this relation. Actually, to prove this takes time. What we need to do is just apply the same properties here. So I just leave here, just give you this as a properties. The last one is also very useful. And this stays here. Okay, let's look at this exponential of Pauli matrix. This is sigma G, right? We are going to use the property of, I think, number 1. And number 1 is not. Okay, so now how to do that? We do this Taylor expansion. So this 1 over n factorial and I alpha some constant to n's power, right? Then now we know the sigma g squared is 1. It's the unity of it, right? The sigma. So now I'm going to separate n to even number and n to odd number. So first one, n equal to even number, or n equal to all the even numbers, right? If I select n from 0 to infinite, but for n any number but 2n is even numbers, among them is even numbers, then here we have for I, let me see, 2n, alpha 2n, right? And sigma g 2n. And the remaining part is n equal to r number, 2n plus 1, factorial, I 2n plus 1, alpha 2n plus 1, and sigma g 2n plus 1. term, because this one equal to I, right? So now we can have n from 0 to infinite 1 over 2n factorial. Here, I squared is minus 1, right? So here is minus 1 to n power, right? This one. And alpha 2n I keep here. This one, right? You may say, okay, it's power, but whatever is power still equal to 0, right? So I just write down here. Yeah, I keep here this one. Okay, so next step. 2n plus 1 factorial. Now here, this one. So since I can separate 2n is minus 1 to n, sorry, yeah, here, minus 1, n, and I, right? This is 2n plus 1. So the I 2n's power is minus 1 to n's power, and the remaining one is I here. And alpha 2n plus 1, this one. This one sigma 2n multiplied sigma j 2n multiplied sigma j, right? Sigma j 2n is n squared is 1, so that is sigma j. Okay. Now I can take I because I is whatever n's power is, so that is does not depend on I take outside. And what is this one? That is a Taylor extension of cosine alpha. Remember this? Here I take I outside, this I, and this one is 5 outside. This sigma j also outside, and then the remaining is sine alpha, right? I can remove I. I need I because this is a 2 by 2 matrix, so this is a 2 by 2 matrix. So this is a relation here is useful. That means we can express this exponential of the Pauli matrix in terms of its function, so trigonometric function, right? Okay, so, oh, I think I assigned homework. I need to give you the information to assign homework. Last homework. 5 is for chapter 5. We can do some practice before it's final exam. 5.6. Only 3. 5.21. 5.30. This includes spin and outward moment. Due is after Thanksgiving, not Wednesday. So I can have enough time to do that. Then that Wednesday, I'm going to grade it, and we will have a last class December 5th. I will return it back to you. Okay, so that is homework. All right, so now let's do some of the examples to how to apply this spin or angular momentum. So now I'm going to do 2 types of examples. The first one, example 1, is if we have a Hamiltonian, okay, is alpha h bar x sx squared plus s squared squared minus 2sd squared minus beta h bar sd, and the s is 3/2. Okay, that is the Hamiltonian. Alpha beta constant. Okay. So the question is, find energy level. Energy levels. Okay, that is solve the eigenvalue. So now that is how to do that. Let's first the Hamiltonian. Okay, since here we have x components, y components, z components, right? So we know as x, x, y, z, z do not commute each other, right? So to do this, it is either if we can manipulate, we write this Hamiltonian such that it is only the s square and sz, then they commute each other, so we can have the joint eigenspace. So because we can rewrite Hamiltonian, how about the x, this part? We want to get rid of these two terms, right? Because these are not like troublemaker. How to do that? Do you agree? X square, sx squared plus sy squared plus sz squared is s squared, right? So this 2 is just s squared minus sz. Then I keep this one. And then this part is okay, right? So then you just see this is s squared minus 3 sz squared, right? Minus beta sz. Okay. So when we deal with this type system, first we try to see if we can manipulate this Hamiltonian such that what happened now H Hamiltonian commute with S squared, right? And the Hamiltonian also commute with SZ. Then S squared, SZ also commute. So what that means, they have a joint eigenspace. We are going to use which one? Since Hamiltonian only the function of spin, no any potential, right? So that spin notation or the quantum number spin only depend on S and Ms. So that is the eigenstates of joint H Hamiltonian S square and SC. That is first, before you go to the details, you first analysis, right? So when this analysis, now the remaining part it becomes simple. Since we know the eigenvalue of S square and SG, so, okay. All right, now what we have to do, so now let's apply. We are going to solve this one, that's be equal to, that is an eigenvalue problem over time interdimensional equation, right? So that is, we are going to solve this. Solve this. So this is a question asked to find, right? After here, I'm going to give an index as ms because this for given states, it will give a given energy, right? So now let's look. Okay, here we already have so H apply S, Ms is so H is here, alpha H bar. Okay. And S square minus 3 SZ square minus beta H bar SZ, right? Okay, so the first one is S square, and this is eigenstates of S square, right? Then that immediately give us the eigenvalue, which is S square S plus 1, right? That one. And then this one here, that is minus 3 SZ. SZ, okay, we just remind you. S square S n S is S bar square S plus 1 S plus 1 and S Z is M S is H bar M S S, right? Just use this. So now S square, we got this one, and SZ is H bar M. So SZ squares twice, right? Okay. That is this first. This one, right? Alpha over H bar multiply this. And now this term. This term is minus beta H bar, and the SZ applied to is H bar MS. Okay, so now let us organize again. So here H bar square, we have alpha. Here I take H bar square outside, right? Alpha H bar. And inside, let me keep another intermediate step. 3, yeah, MS square, right? Actually, yeah. And then this is a H bar cancels, so minus beta MS. Okay, let's just keep that. So let me this one here and this. Yeah, to give this one so this is cancel and that one is so. Okay, just whatever I have here, so let's do this. Okay. So that's equal to energy here, right? Energy, let's compute. Now we have the energy is dependent on S and MS, right? So given different, S is fixed, 3.5. MS depend on is we have 4 values, right? So that means equal to alpha H bar, that is S plus 1 minus V MS squared, and then minus beta MS. I just said if this is a dimensionless, here we have H bar, so I think so I didn't say dimensionless, I just said constant, right? So that's fine. Okay, so now depend, right? So S equal to 3.5. And MS, if let's MS take this, let's take the from lowest. Then here, the 3.5 and 3.5 is a 5 bar, right? So 15, right? 15 over 4. So here, this is a 15 over 4. And then this one is square, so I just give you the numbers. You can just minus 3 H bar alpha plus, because the minus and plus, right? Plus 3 over 2 beta. That's for this case. Then S always the same. Now MS by increase 1 unit is minus half. So this one is 3 H bar alpha plus half of beta. You can discuss, actually we have 4 values, right? Depend on MS. So that is 3 H bar alpha minus half of beta. The last one is minus 3 H bar alpha. Okay, so we obtained all the energy levels in this case. Then you can see they are non-degenerate, right? By giving different MS, they have different values. So this is one example, simple case. Now let's do a little complicated case, a little challenge case. The challenge case is now suppose we have a spin of electron s. Okay. But then in the direction of arbitrary direction n. So now this number 2. Find the eigenvalues and eigenstates of the spin of electron as in the direction of a unit vector impact. Okay. Then how to do that? Library is to solve the eigenvalue problem, how to solve it, right? Okay, so here, this let's consider 3 dimension, right? So that is n. Suppose it's arbitrary vector, unitary vector here, n. And we have s. So ask us, if s along direction project to the direction, that operator, and c along that direction, what is eigenvalue, about eigenvalue and eigenstates? Okay, we know s square and sz, right? We know the eigenstates. So how to do it for the arbitrary case? Okay, the idea is like first. The question is, I use height, right? This I'm going to say as z operator. This is the operator of the electron or spin operator s along the direction of unitary vector n, which is arbitrary. So this is this one, and the question is asked to find solve the eigenvalue problem, right? That is, we have the operator, and we are going to find the eigenvalue for this operator and eigenstates. So that is key. That is the question asked us. Now first, we need operator. The operator means is project along the n hat direction. Okay. So once we know the operator, we are going to solve the eigenvalue problem step by step. All right, how to obtain this one? Let's first, S is S, the spin operator is vector, right? As X components, Y components, and Z components. Right? N unit vector is also the vector, right? Vector, if I define this as a theta, this is a phi. So we know the unit operator is sine theta, right? Sine theta cosine phi along the I direction. Sine theta sine phi is y direction, and cosine theta is z direction, right? Okay, so we know each individual vector, then the Sn is S inner product n hat. So now inner product, because we in the Cartesian coordinates, then this is the x sine theta cosine phi, sy sine theta sine phi, and plus sz cosine theta, right? Now we can use this. Okay, now this is the first we write down. Now, for the electron, S equal to what? Half, right? Again, this is half. So when we say electron, I mean that's in chapter 7 we'll mention again. But here I think I already let you know when we discuss the allowed G value, which is, or allowed S value is 0, half, over 1, or 3 half. And for all the integer, odd integer, half, odd integer numbers are fermions, and electron are fermions, right? So that is electron. Just remember electron spin is half, right? But we can with it. So because this, so in the matrix representation, we just discussed before, matrix representation, we are going to use matrix representation to solve this eigenvalue problem. Sx half h bar, right? 0, 1, 1, 0, right? Sy is half h bar and 0 minus I minus I 0. Then Sv is half h bar 1, 0, 1 minus 1. Sorry, 1, 0, 0 minus 1. So we substitute into here. Substitute those matrix into here. So Sn is, okay, here I keep this some trigonometric function here and multiply half h bar 0, 1, 0, sorry, 0, 1, 1, 0. And then the second one is y, right? So that is sine theta cosine, sorry, sine theta sine phi, half h bar. And then we put inside the matrix 0 minus I 0 and plus cosine theta half h bar 1, 0, 0 minus 1. Now we can compile together because this all together be 2 by 2 matrix. So the matrix element here, I take the half h bar outside, right? It's all half h bar. And this in this is 0, right? So this term only this one, right? So that is cosine theta. And let's do the same thing. This diagonal is minus cosine theta. So because x and y, there's no diagonal term. Then this term. So this term you have this one plus minus I, right? So that is sine theta cosine phi plus minus I sine phi. Right? This is minus. Then this term is again is sine theta and then cosine phi plus, right? Plus I sine phi. So this is a 2 by 2 matrix for Sn. Then we can do the further. Because this one is exponential, right? So that is h half h bar and cosine theta, sine theta exponential minus I phi, and this is sine theta exponential I phi minus cosine. So now we can very simple or clear the matrix. Then the remaining job is solve this matrix by solving the eigenvalue problem. And in chapter 2, we already studied for the eigenvalue problem in the matrix representation. What we should do, you can also do the homework. Right? So now, so S n lambda lambda. This one is became cosine theta sine theta. This became here, right? I mean, now even though I use head, that is a matrix. So the solution, if you remember, solution for the solution for this is just a solution. Okay. For lambda is we are going to do the Cadirect equation. Right? We are going to solve this to find the allowed lambda. So this means, okay, we have, be careful in this case, this half h bar is keeping, do not miss this one. Even though in the matrices we can take outside, but we have a lambda here, so that be half h bar cosine theta minus lambda. Sometimes you miss this half, okay? And then this sine theta exponential minus I phi, and sine theta exponential I phi, half h bar here, sorry, minus, right? Minus half h bar here, cosine theta minus lambda. We're going to find this. And here, then this one is, mathematically we can solve this one easily, right? So minus half h bar cosine theta minus lambda minus sine square theta, because this is cancelled, right? Sorry, I think I also missed this one. I also missed here. Also, see, I also made mistakes here. We have h bar square over 4 sine. So the solution, this one multiplied, well, you can take the negative sign. You have a negative h bar square over 4 cosine square theta minus lambda theta, right? Minus h bar square 4 equal to 0. So you can see here, you have this one is minus cosine square, this minus sine square is 1, right? So you have a lambda, easily lambda square is, so lambda is plus minus n. Okay, so we obtain this eigenvalue. So that means when we deal with this basic representation case, well, this in, right? We are going to solve the eigenvalue problem by first find this characteristic equation to obtain the eigenvalue. That is the first question, right? Find eigenvalues. Now we're going to do the eigenstates. Eigenstates is a little bit time consuming. You have also do some homework. So now let's play with this. And just try to remind you and how we did before now. Now for the eigenstates. This eigenvalue we already obtained, so that is okay. Eigenstates. First, for lambda equal to, let me see, this half, right? Okay, let's consider. All right. So we use the plus minus to distinguish these two eigenvalues. For this case, now we're going to solve this. We're going to solve this this one, right? So we're going to substitute this. Then there is you're going to solve Sn lambda equal to lambda. So now we are going to find these states, right? So that means here Sn we already have here. And half h bar cosine theta sine theta exponential I minus I phi sine theta exponential I phi and minus cosine theta. So here we are going to find this matrix element, right? Lambda plus. And then lambda plus is a half h. So we are going to solve this equation. Here now we can cancel. Then we have a cosine theta, right? And plus b sine theta exponential minus phi equal to a, right? To this. And then the second one, a sine theta exponential phi minus b cosine theta equal to b. Yeah. So from here, we can find the relationship between a and b. So now let's just take a here. Okay. I move this term to the right hand side. So a1 minus cosine theta equal to b, right? B is sine theta exponential minus 1. And this one is twice of sine square half theta, right? A multiplied 2 sine square half theta, right? This one. And this one, remember, is twice of sine half theta cosine half theta. Then you can see here, we can cancel this one, right? And this one. Factor 2 cancel. So you have a and b is, they have a sine, but you have cosine of b cosine theta. Sine, we have cosine. Let's put that. Okay. Now we have the lambda, and before normalize is a, b is a cotangent of theta exponential alpha. So then we are going to normalize. Okay, normalize, that is a square plus a square cotangent square half theta. This one is 1, right? Normalize this multiply is conjugate, so not equal to 1. Then you can have a square is cotangent square theta. And that is, we can multiply the sine, denominator sine square half theta, right? So sine square half theta here, and that is 1, so that is that makes sense? Yeah. Okay. So we have a normalized states is here. Okay, I have to make it. So A is sine. You say that you can have plus minus, let's take plus, right? So because what plus minus b has a relation with this, so that sign is just scaling factor or some constant. So now here A sine theta, B is here, right? So, okay. So this is AB, so B is cotangent, right? Sorry, this is cotangent tangent. I just reverse. So then you can see A is a sine, then the sine is a cancel this. Did I make a mistake? This be cancelled. One minus the sine, right? I think that is. Did I wait a moment?
Cosine squared?
It's minus, right? Here is minus. Yeah, but this is correct. Yes. Okay. Did I? So let's see. So this is sine. The size. Did I not cancel? What is the Did I? Oh, I think A equal to B, A divided by sine, so that is called that's correct. And B is a tangent. That is also correct. Tangent is sine, cosine, so this is sine. Did I get this? Is a sine, is a cosine. This is cosine square, sine square, and go to sine. I think this one. That is correct. Whatever. If not, if this is correct, then that is sine square, half cosine. Not square, yeah, square. And exponential phi. Because this is sine, cosine, right? And then this is sine. So. This should be very symmetric.
Is it because in your matrix at the top, you put A in for B at the top in the middle?
Yeah.
At the top, the lambda plus, should that be the B at the bottom? The tan?
Yeah, B. Oh, okay. Yeah, you're right. Yes. Yeah. Thank you. It should be this one, right? It should be tangent. You're right. Because that's B, yes. So then here, this is the tangent, yes. I started very high. Thank you. So this is the tangent instead of cotangent. So now this is cosine, not sine. Yeah. Cosine square. So A is cosine. Now we have, thank you. That is cosine of theta. And then now A is cosine, so cosine goes into sine. Okay. I think similarly to do this similar way for lambda negative or lambda minus. And you still have solve this lambda minus equal to lambda minus. And then you have h bar, half h bar cosine theta sine theta exponential minus I phi sine theta exponential phi minus cosine theta. Here A prime B prime equal to negative h bar of A prime B prime. Okay, the details I just gave you some of the relation between, so we have the relation between that is A cosine theta plus B sine and this side is same. This is between minus this part is same. And this is an A cosine sine theta. Exponential phi minus B cosine theta equal to minus B. So we have minus A plus cosine theta equal to B sine theta exponential minus phi. This one is 2 cosine square half theta. This was again sine half theta and sine half theta, right? So we cancel the cosine, minus cosine, and then we have a minus side. Then you have a B is minus A cotangent half theta exponential minus phi. here, this is a plus, plus n. So then normalize what give us A, I just compute the result, give A is, what is the cosine given sine? And so then the B is minus sine theta cotangent of theta exponential phi. Yes, that is give us minus. Okay, I already gave A, right? So I need this. Just direct substitute here. That one, so sine, so that is minus. Then this. Then finally, normalize. Plus sine of theta minus cosine of theta. Okay, so we obtained the eigenvalue and the eigenstates. Now, just think about. So if n is on the x, y, do the same thing and see what kind of what is lambda. Follow same scale, but the direction is different. Okay, just let you extend your idea. So now we finish the spin discussion, the general theory of spin, and do the example for the spin half. So now we can go to another type of this important angular momentum, which is orbital angular momentum. In this case, we already know the orbital angular momentum, but we are going to find the eigenvalue and eigenstates in the position representation, the details. So now let's go to the next topic.
I have a question for
Yeah.
you. Why is spin in 2 dimensions?
This is a half. Why spin in 2 dimensions? That is arbitrary. You see here, spin can be here, can be line as y, can be line on the y-axis, any direction, arbitrary. Or this is a spin. You can select your axis is with this 2-dimension like spin line on the plane, or you select 3-dimension is up to. So spin is a direct, is vector in any arbitrary direction, right? So it can be plane, can be line in the xy plane or xz plane or yz, or can be in the 3D, 2D, and maybe 1D if you select only another direction 1D.
So it's possible that we'll see eigenvectors that are 3 dimensions for spin, that are
Eigenvector, yes, it depends on different, how you select to represent. But the eigenvalue you will see it will not depend on what selection.
Okay. At what point did we make the selection this time?
Just say the point is that if we look this system like either electron or proton or photon, whatever has a fundamental particle in the space, and ask you to find this space.
I didn't mean point as in the reason. I meant like at what step in our process here did we, because we never implicitly said we're considering 2 dimensions. At what point in our math did we end up making ourselves be in 2
It's
dimensions?
this one.
But we did describe n in 3 dimensions.
So you can also describe it in 2 dimension.
But my confusion is that at the very beginning we said that n was in 3 dimensions,
Yeah.
and we end up with spin being in 2 dimensions.
Oh, okay.
So
No.
we,
This is, I just assume this this we already finished, 3 dimension. So I just gave you a think about if n is not on 3 dimension but 2 dimension.
right, but you
How
said
so?
that's 3 dimensions, but the the vector is only two-dimensional. You see my question here?
Yeah. I mean, this is a unit vector, so this n either here or here, if this is an x.
It's a result of it being spin 1/2, because there's only two possible values that it can take, so it's a 2 by 2 matrix.
This is a spin, arbitrary direction, right? Spin here. Then you set up your coordinates. So I'm interested in is this spin projected along n direction. So n maybe here, maybe here. N is arbitrary, or maybe here, right? So if it's on this xy plane is a 2-dimensional, that means you are going to project S to here. Then solve the eigenvalue problem, or to here. So that is arbitrary. I just select very arbitrary 3D. But if a particular case 2D,
Okay.
then what you need to do is write in terms of 2D. If xy, you just write down the x component, y components of n hat. If on this xz, you just write down n in terms of this x component, z components. And then once you have this, you can find as n, right? Then when you have this one, you're going to solve the details. Okay. That is the, I just select my original, so then for the specific case, it became a bit easier than this one, right? Because this is 3D means you have x, sy, and sz, 3 put together. In a 2D, maybe sx plus sy or xs plus sz. Okay. Now, we are going to go to the another topic is eigen function of orbital angular momentum. Here we discuss general angular momentum, and when introduce, we focus on spin. Now we focus on orbital. So, orbital first, general property, general feature. General feature means all the angular momentum features we also applied here, right? So first it is, and now we are using L to represent or express orbital angular momentum. Use S as spin and use G as a general. So L, spin, vector, right? Now, again, it is vector, so we have 3 components. This is for general for spin for the orbital ORC, right? Then we can introduce plus minus similar things. This is Lx plus minus Ly. The lowering and raising operator. Then we have a commutator relation. So L now J, since you already familiar with it, K is I H bar epsilon J K L L L. Now you know this meaning, right? So you know this commutator relation. Okay, so this one, and then we know the L square always commute with any component. Then, since we introduced L plus minus, so we have also the commutator or commutation relation between the L plus and L minus, follow the same thing as the general. That is 2h bar LZ. Then the LZ is the L plus minus is IH bar L plus minus. These are all followed. Whatever spin angular momentum, orbital angular momentum, and the general angular momentum all are followed. Okay, then the eigenvalue. So we know. Okay. Because let's still select the z components, L square and LZ commute, so we select joint eigenstate. The notation is we use L and ML to distinguish M. G, if you use G, is general. And M associated with the components of G. So if it's spin, we use S, MS, but for orbital angular momentum, we use L, M, L. So L square is this eigenstates of L square, so that gave us H bar square, right? Remember J multiplied J plus 1, so now here's L, L plus 1, L, and L. LZ is also eigenstates of LZ is appeared H bar and L, L, and L. Then this L plus minus, similar result, we have H bar, okay, square root. Let me use this one there. L plus 1 minus M L plus minus 1. And L, but M L plus minus 1, right? So with this, so we have Lx. Lx is half of L plus L minus. So you have two terms, right? That is half of H bar. Okay. We have two terms. One is L plus, so let me go in parentheses. L plus 1 minus M L. Here, since plus is M L plus 1, L M L plus 1, and then plus L plus 1 minus M L minus 1. L minus 1. Ly is half I over L plus. L plus minus L minus. And that gives us inside is L plus 1 minus M L plus 1. And here L plus 1 minus this M minus 1. Okay. Those are all general. Now, next question is we know for given L, M L is clear, right? Minus L plus 1 until L minus 1 to L. 0 or, sorry, I'm just clicking question. Because we know J can be either 0, half, 1, 3 half, and 2, any integer number or half odd integer number. And the spin, for each spin, this fundamental particle also has a fixed S. How about here? The L is allowed all values, all the integer and the half integer, odd integer or just integer. Here is the question we are going to answer. Okay. Oh, sorry, already passed. Okay, so we on next Monday we still have a class before the Thanksgiving, right? So in that class we are going to discuss details about how to answer this question and also find the eigenfunction in the position representation of object.
Let me see if I understood your question. Whenever you want the projection
You
into
talk to me, to him, right?
yeah,
Oh, okay. Sorry.
in
All
the
right, I keep
2D,
it. Yeah.
so you have the XY two-dimensional matrix, the 1/2 operator, the spin operator, it is forced into a 2D representation because it's a 2D matrix. You can't have the spin operator.
So you found the heart of my question. Why is the spin operator in two dimensions?
Because you can't multiply a 2x2 matrix by a 3x1 column matrix.
That question is for spin half. Spin half is a 2x2 matrix because we have only 2 eigenvalues, right? So the matrix representation in the eigenstate that's be 2x2. If a spin 3/2, that's 4x4. If 1 is 3x3.
Well, I guess the seeing that the
Yeah, that is spin equal to 1.
Then you can
You
have
need a hyper h bar before that.
then you can have the x, y, z. That makes more sense in the
Yeah,
3D in my head.
no, okay, that is not related to 3D.
It's not.
That's different. So the vector, the vector can be, if in the matrix representation, this one you can be 2D, 3D, 4D. It depends on. That is, so if S equal to half, we have only half
Two possible.
yeah, 2. So the matrix, this space spanned by this one, only 2 basis vector.
that part I get, but
So that is 2D. But this 2D is matrix represented. This one is vector project on the plane over 3D.
Yeah.
They are different.
Right. That makes sense.
That make sense?
so you're saying that spin is necessarily exists on a plane.
Not that, maybe sometimes I can have spin here in this direction or this direction. It's up to you.
The dimensions of the spin are not a 1-to-1 correspondence
To
with
the
spatial dimension.
yes. This is space. Okay, that's key word. This is spatial vector. Spatial only have 2D. Sorry, 3D, right? In general, or 1D is one direction along x-axis, or along the xy plane over 3. Over 3. So that is the 1D, 3D, and 2D, 3D. That is called this space vector.
I'm not concerned about
Okay,
that.
this one is the matrix. Which dimension matrix depends on which. When we have a matrix, we have a basis. Just use general. So that's how many I maybe 1 plus 1 dimension. If I equal to 1, 2, that's 2. So this is 1D. This is 2D. If I equal to 1, 2, 3, this 3D. But this one is given you this the matrix space. Then any even for this one you can represent that. So like one dimension like function, right? So like fx.
I always get caught up trying to differentiate between dimensions of the basis and dimensions of space because I'm
Yes.
so used to working in 3D XYZ, but the vector for the spin is made up of independent basis vectors, and for spin 1/2 it takes 2 basis vectors. For spin 1 it takes 3 basis vectors.
Yeah. The basis vector is also arbitrary. We can select eigenvectors as a basis vector. We can select others.
Right.
When we select eigenvectors, depend on how many eigenvalues. Complete set, right? We have, if you select this one as a basis vector, it must satisfy this, right? Say, sorry, equal for given s and s equal to 1. And then they also have orthogonal. If satisfy this, any side of this cat can form this space. And this space is in the n dimension. Whatever even this one dimension, the dimension may be n dimension. But in any dimension, you can represent the vector in this dimension. So that is the difference. I think you learn because you learn this theoretical mechanics, so we have the general canonical variables, right?
Yeah.
Even for this this one system, but we have different variables.
It's very counterintuitive, but I'm starting to understand the difference
Yeah.
between how you make up a complete basis.
For example, here in the chapter 4, we just study all the one dimension. We say one dimension system is only have the motion is along x, only along one direction, right? So that is the motion or space. You say space is 1D. However, we can solve a lot of eigenstates, right? I may be in a discrete number, whatever. Then each group, we can form the space. This space, you see we have one, for example, the infinite potential well is go to infinite.